Welcome to our channel. Today, we're diving into a radical shift happening in modern commercial cultivation. It's a method that is completely upending how we think about waste, soil health, and maximizing the genetic potential of our plants.
Right now, there is a highly provocative operational philosophy quietly circulating among vanguard commercial cannabis cultivators. The mindset basically boils down to this: why I'm burning my harvest waste to double next run's yield. I know, it sounds completely counterintuitive, right?
And that brings us to our central mystery. Why on earth are top-tier commercial cultivators deliberately setting their harvests on fire? Traditionally, growers fiercely protect their organic matter, always looking to return it to the earth. Yet some of the most high-tech, advanced operators out there are now incinerating it on purpose. We absolutely need to understand why this is happening. But before we get to the answer, we have to look at the massive problem they are trying to solve.
Look, after a commercial facility extracts the high-value flower, they are left with a massive physical and financial nightmare. We're talking about hundreds of pounds or kilograms of tough, fibrous stalks and these massive, dense root balls per harvest cycle. This post-harvest waste takes up an incredible amount of space. It becomes a huge operational liability, and the municipal landfill and disposal costs, well, they are simply astronomical.
Because of this burden, there's a massive ideological clash currently dividing the industry. On one side, you have the old-school organic soil builders who champion traditional slow composting. And on the other side, you have high-tech controlled environment operators who are turning toward extreme thermal environments.
To really understand this high-tech shift, we need to break down the romanticized myth of standard composting. Honestly, traditional composting is incredibly inefficient for a dense, large-scale monoculture. First off, it's highly space-intensive. Those dense, woody stalks can take anywhere from several months to a full year just to break down. And more importantly, it has a fatal environmental flaw.
You see, slow aerobic decomposition relies on bacteria and fungi eating the organic matter. But as they do their job, they release massive amounts of carbon dioxide right back into the atmosphere. This off-gassing completely negates the incredible carbon sequestration potential the crop initially achieved during its vegetative growth.
And the problem actually doesn't stop with CO2. Traditional composting, especially if the pile gets too wet and becomes anaerobic, generates methane. Methane is a greenhouse gas significantly more potent than carbon dioxide, which further destroys the commercial operation's carbon footprint. But for a grower, the absolute biggest risk here is biosecurity. If a massive commercial compost pile fails to reach reliable thermophilic temperatures, meaning it doesn't get consistently above 140 degrees Fahrenheit or 60 degrees Celsius, lethal soil-borne pathogens just survive. We're talking about facility killers like Fusarium oxysporum and Pythium. These cause catastrophic root rot and vascular wilt. They literally lie dormant in those decaying root balls, and if you use that compost, they will wipe out your entire next cultivation run.
So, that leaves us with a critical question. Is there a way to neutralize this severe biological threat while actually upgrading the agronomic value of the waste? Well, let's pivot and look at the extreme alternative.
Enter ultra-high temperature pyrolysis. This is a violent, extreme thermal environment that is completely devoid of oxygen. The waste biomass is placed into a reactor and heated to a staggering 1472 degrees Fahrenheit, which is 800 degrees Celsius.
The crucial takeaway here is that hitting these extreme temperatures acts as a definitive biological firewall. In this oxygen-free inferno, every single pathogen, viral load, and fungal spore is instantaneously eradicated. You are left with a 100% sterile material, but you aren't just left with a pile of ash. What comes out of this fire is actually a highly ordered crystalline matrix that is completely unique to the cannabis plant's biology. You see, cannabis is a hyperaccumulator. It actively pulls massive amounts of heavy minerals like calcium, potassium, and magnesium from the soil. So while standard wood biochar just gives you low ash and standard moisture retention, this specialized hemp matrix features up to 3 times higher moisture retention capacity and incredible structural stability. And this brilliantly illustrates why that crazy stability exists. It's due to a botanical anomaly involving silica phytoliths. During its vegetative growth, the cannabis plant actively absorbs soluble silicon from the soil and deposits it as solid, rigid, microscopic structures right inside its cellular walls. It does this to build immense mechanical strength for the stalks. Now, here is the truly surprising fact. When you subject these stalks to 1,472 degrees Fahrenheit, the extreme heat burns away all the organic polymers like cellulose and lignin.
But those silica phytoliths, they survive completely intact. It creates a fossilized 3D replica of the plant's biological capillaries, a literal crystalline silica honeycomb. Please like and subscribe, it really helps our channel a lot.
So now, we can finally reveal the core solution to our initial mystery. Why do these top growers burn their waste? Because they are utilizing a 4-step closed-loop system called the biochar waste loop. This is exactly how high-tech cultivators turn a massive liability into a regenerative yield multiplier. Let's break down exactly how this loop works. Step 1 is supercritical CO2 extraction. Before burning anything, the waste biomass actually still has leftover cannabinoids and waxes. By subjecting it to supercritical carbon dioxide at pressures of 150 to 250 bar, that's roughly 2100 to 3600 psi, at mild temperatures around 86 to 122 degrees Fahrenheit or 30 to 50 degrees Celsius, operators can safely strip out the remaining high-value compounds. And because the CO2 evaporates completely, it leaves behind a pristine, solvent-free material with zero toxic chemical residue. Once that pristine material is pyrolyzed, it transforms into what agronomists call the structural battery. This highly porous, stable carbon lattice acts as an absolute agronomic sponge. It permanently alters the soil's hydrological dynamics, holding on to moisture and nutrients like a permanent subterranean battery.
But there is a very crucial catch here: charging the battery. Fresh out of the kiln, raw biochar is a sterile, empty void. If you put it straight into your soil as is, it will aggressively suck up all the water and nutrients, temporarily stunting your plants. So it must be inoculated, or charged. Cultivators do this by soaking the raw biochar in rich compost teas for 24 to 48 hours. Its expansively negatively charged surface tightly binds to positive nutrient cations like calcium and magnesium. This exponentially increases the soil's cation exchange capacity, preventing your valuable nutrients from washing away during heavy irrigation. Once charged, this incredible carbon matrix acts as the ultimate microbe hotel. Remember those fossilized microscopic pores we talked about a minute ago? Well, they happen to be the perfect, exact size to provide a physical sanctuary for beneficial bacteria and mycorrhizal fungi. Tucked deep inside the biochar, these microbes are safely protected from soil compaction, extreme temperatures, and predation.
So let's bring those two clashing industry ideologies back together. We had the sterile safety and speed of pyrolytic sterilization on one hand, and the rich, living biology of slow composting on the other. What happens when we actually combine them?
We achieve a synergistic breakthrough known as co-composted biochar. Cultivators are now mixing this highly porous, sterile biochar directly into their active green compost piles. The biochar provides incredible aeration and immediately traps the volatile greenhouse gases, absorbing all those nutrient leachates that normally just wash away. This drastically accelerates the biological breakdown process, resulting in a perfectly balanced, supercharged living soil amendment.
And this brilliant synthesis really matters because of the massive environmental footprint of the alternative. Traditional indoor cultivation that relies on synthetic inputs and disposable media, like peat moss, has a massively destructive footprint. Believe it or not, it can generate up to 5,200 kilograms of CO2 equivalent. That's over 11,400 pounds of CO2 for just a single kilogram or 2.2 pounds of dried flour.
By closing the loop with biochar, we connect the dots to achieve the yield multiplier effect. This permanent structural battery completely replaces expensive, disposable inert media. It drastically reduces water usage and drought stress and eliminates the need for harsh synthetic fertilizers. By removing abiotic stress and nutrient lockouts, the plant doesn't have to work as hard foraging for food. It conserves massive amounts of metabolic energy, redirecting it purely into explosive vegetative growth, maximizing its genetic potential for cannabinoids and terpenes. It literally doubles the efficiency and yield.
And that is the true power of the regenerative bioeconomy. By embracing extreme heat, high-tech cultivators have figured out how to turn their heaviest, most expensive operational liability into a permanent structural battery. It transforms the whole facility into a highly lucrative, carbon-negative powerhouse. Thanks for watching. This content does not constitute medical advice, legal advice, or recommendations for the use, self-treatment, or consumption of any substance.